Hello. I feel like being a little crazy today, so I'm going to use a whiteboard for today's lesson. So we have two kinds of integration techniques today. The first one I'm going to call tricky substitution. We did, I think, learn this last year, substitution. Sorry, but I don't remember. So I'll treat it as if kind of we didn't. So we're starting to accumulate these integration techniques. We've integrated, straight up normal problems that we have formulas for. We have integrated, my gosh, I'm staring outside at the rain. It's so gloomy. We've integrated stuff that we need to manipulate first or reduce first. We've integrated by substitution. Haven't gotten super gnarly with that, but I think we've done probably what we need to do. So this is another form of substitution where there's a little bit of a trick involved. So an example of this would be a problem like this. Okay, so let's say I have this as my integration problem. The first thing that I would do if I'm looking at this is I would think, like, is there any way for me to make this simpler and be able to do it? But the answer would be no. This is to the first power. This, though, quantity would be to the 1/2. I can't combine them real easily, or I can't combine them, period. So I use substitution. So I'm going to do what I normally do and just say I'm going to let u equal the innermost part and just see what happens. I mean, sometimes you go down a path and it's wrong, but a lot of times if you kind of follow what you're supposed to do, it ends up turning out just fine. So if we let u be something that's on the inside, the derivative of u would just be 1 dx. So if we're substituting, we'd start going through and saying, okay, here's the integral. This is going to be the square root of u. But we're a little bit stuck because du has to be dx, which is just this. But I have extra stuff. And my extra stuff particularly is an x. If my extra stuff was just a 5, that'd be fine. I would just bring the 5 out to the front. But my extra stuff is a variable. So that's where I want to turn to, okay, well, this is still dx, I'm sorry, du. But what should I do about this? Well, here's where the trick comes in. I want to take u, and I just want to manipulate this and solve this for x. Because if I solve this for x, I'm going to get that x is u minus 2. What if I take that and replace that with my x here? So what if I substitute in x for what x is based on what I've chosen for u, and I say, okay, well then x is going to be u minus 2, and I still have a minus 1. Does that make the problem doable? The whole thing with substitution is I'm trying to make my problem doable. It's not doable up here, but is it here? Well, here I have u minus 3 times u to the 1/2. Well, it's not doable as it looks now, but now I can distribute this. And I can have the integral of u to the 3/2 minus 3u to the 1/2 with respect to u. This is doable. This was not. This couldn't distribute the way it was because it was a quantity with a power of 1/2. And at least if I tried to distribute it, it would have been really pretty ugly. I guess technically I could have, it just would have really gotten nasty. So when I use substitution, I get down to something that if I had gotten this problem from the start, I would have said, oh yeah, let me just distribute this and have two separate terms and I can integrate them each separately. So that's what I'm going to do now. So the integral of u to the 3/2 is u to the 5/2 divided by 5/2 or times 2/5 minus 3u to the 1/2 will be 3u to the 3/2. Instead of divided by 3/2, it's going to be multiplied by 2/3 plus c. So let's put this a little bit together and make it look better and put my u's back in. So we're going to have 2/5 times, go back to my u, x plus 2 to the 5/2 minus, reduce this to x plus 2 to the 3/2 plus c. There is my final answer. Ugly, but true. Okay, let's look at another one like that. Let me just get my notes out so I have it. So part of the hard part is going to be picking up on when we use all these things. When do we use substitution? When do we try to simplify the problem first? Well, I kind of go in the order that we learned them. When I first get something, I try to do it without substitution. Can I manipulate this? Can I reduce this so that it can be easily integrated? Like this, I actually could do some manipulation. I probably could. No, I still couldn't. Yeah, it would be really difficult to do. So tricky substitution is your next bet, or substitution in general is your next thing to try. All right, let's try this one. Okay, if I were looking at this, I would probably think, I don't know, that it's use substitution, but I have a squared, which is a little confusing. But even though I do have something squared, I have this entire thing under a root that is going to be what I choose for my u. I'm looking really for a quantity that's within something else, or a quantity that's on the bottom, which doesn't really happen with tricky substitution anyway. So du is going to be 1 dx. Okay, so when I go start to replace everything, I have the square root of u, dx is just du, but I have this extra left over. And I have no way, at least with this straightforward appearance, to get that replaced. But I can solve this for x. So x is going to be u plus 2. So I can put this in for the x. Just for giggles, I'm going to square this over here because I didn't leave myself much room. I might have to erase anyway. So let me solve this for x squared. If x is u plus 2, x squared is u squared plus 4u plus 4. And then therefore x squared plus 1 is u squared plus 4u plus 5. I'm going to put that in here. Okay, doesn't look a whole lot better, but this can be simplified. This is u to the 1/2. That can be distributed. So I'm going to have u to the, remember I'm adding exponents just to put them together. So 2 plus 1/2, this is 4 over 2 plus 1 over 2, so 5/2. Plus 4u to the 3/2 plus 5u to the 1/2 with respect to u. Now I can integrate, so I'm going to have u to the 7/2 times 2/7 plus u to the 5/2 times 2/5. So I'm going to make that 8/5 because of the 4 that's already there. U to the 3/2 times 2/3 plus c. And then I have to go put u back in. Oops. Gross, annoying, gross, gross, annoying. There you go. Sweet, tricky substitution. So that was the first thing I wanted to go over today. That's not too bad. The second thing is how to take integrals where inverse trig is our answer. I'm going to, on the classroom, I'm going to be posting a new updated formula sheet because, you know, I've never really taught the integrals of inverse trig because it doesn't show up a ton on the Calc or the BC test, but because we have the time, I want to make sure that we get everything in that could show up. So I updated this and I posted it to the classroom, and I updated these 3 formulas. So I had written before, save these for later, and now we're going to go ahead and we're going to look at them. So I had only put like a rudimentary example on the first one. Now it's updated and it looks a little bit better because the way we're going to see inverse trig is going to look a little bit more complicated than we would like. So you don't even need to write this down, but just watch for a second. If I had the integral of 1 over 1 plus x squared, that's really straightforward. That's arctan. Okay, and if I had the integral of 1 over the square root of 1 minus x squared, that's also straightforward. That's arcsine. But the problems that we're going to see are going to have some other numbers. Maybe they're going to put a 5 up here. Well, that doesn't change anything. I can just pull that 5 out to the front and then have a 5 in front of my answer. That's easy. But what if they make this something else? What if instead of 1, what if this is like a 4? what the heck do I do with that 4 in terms of the solution? Like, where do I put it? Well, we actually have some formulas for that that help us not have to think a whole lot and be able to undo inverse trig when it looks like that, when they stick a 4 here, or if they put a 3x squared there. So there are some ways to help us undo that chain rule without having to go through a whole lot of trouble. So these formulas, you do not need to memorize, at least not yet for this class. Okay, I think that on the AP test, they will require that you know it. But for right now, there's no point in sticking this in your brain since the AP test isn't for a long time. So we have a formula. When I see this kind of integral, a squared minus u squared. So instead of just 1 minus x squared, there might be more than that. A might be something that's not 1. U might not just be x. This is the formula I'm going to use. When I see tangent, if I see a problem that looks like this, remember tangent's usually 1 over 1 plus x squared, but now this could be something else. And the formula is going to look like this. Basically, this formula is allowing us to like do our substitution and do our inverse chain rules without having to give it a whole lot of thought, with allowing us to just follow a formula. I'm going to put arcsecant down here too, but I am totally looking at the formula right now because I do not remember what it is. And part of the reason I don't remember is there is no way the AP test is asking you to do that. So I won't ask you to do that either. But I thought for those people who wanted to see it, there was the formula. So do what you want with it, but we do not need that one. The other two, it is possible that they show up on the AP exam. So let's go through a couple of examples of how this is actually going to work. Again, those formulas are on the Google Classroom. You're going to want to definitely have that marked. I even actually just put it in my own notebook with like a little tab so that I can quickly reach for it when I want to reference it, because every once in a while you want to double check yourself on something. Okay, so for example, is my voice weird when I talk on this? I feel like I'm using a weird voice. Oops. Okay, let's say you have this. Again, when you get a problem, it's really hard to know what are you supposed to use. So let me just go through, let's say you got this problem today, you really aren't thinking about inverse trig, and you're like, okay, well, you can't do the problem the way that it currently looks, so I would let u equal the bottom. Don't write this down. Then I would let du equal 18x dx. Well, I'm stuck. I don't have, like, here's my u. Again, I'm going to be erasing all this red. Do not write this down. I would have u in the bottom, but I don't have what I need on the top. I don't have 18x dx. I just have dx. I can put an 18 in. That's fine, but I don't have an x. And once I need an x and I don't have, I can't insert it. Okay, I cannot insert an x into a problem. I can't just multiply by x and then divide by x out front. Cannot do that. That's illegal. The only adjustments that I can make to a problem are with constants. I can put an 18 in and therefore multiply by 1/18. But I can't do that with variables. So I'm stuck here. If the problem had given me an x on the top, then I wouldn't be stuck. Then I would have a 1/18 out here, and this would be my du, and this would be a natural log problem. Okay, if I had an x given to me, this would not be inverse trig. This would be substitution, and your answer would be a log. U would be the bottom, du would be basically the top. I just have to insert an 18 and a 1/18, and then I'd be good to go. But that's not what this is. I was actually pretty excited to do this because I feel like it's the first thing that you've seen so far this year, and it's already the end of October. That's brand new. Let me write that up again. I'm excited to move into new stuff. Okay, so since we cannot let the bottom be u, it doesn't work. It's not so there's nothing I can do to simplify this. Somehow in the recesses of my brain, I'm going to have to bring up inverse trig. So this looks a lot like inverse tan. Inverse tan is usually 1 plus u squared, but now I have this formula. So my formula is, if I have the integral of du over a squared plus u squared, this will equal 1 over a times the arctan of u over a plus c. So I need to identify what is a and what is u. That's okay, I can do that. So this is, so my problem has to look like this. I've got to get my original to be set up like this. Well, what would a be? If this needs to be a squared, then this a would be the square root of 2. Because this would be the same thing as dx over, instead of 2, I would write the square root of 2 squared. Okay, so a would be the square root of 2 to make my problem fit the way the formula needs to fit. And then u would be 3x, because u also has to be squared. So this is only going to work when I have a term here that can easily be broken down into its square root. So the quantity 3x squared works, and now this is kind of set up like this. But I want to actually use a and I want to use u because of this one little tiny issue, which is I can't just take the integral like this. I have to also consider what du is. If u was just x, you could go straight to the formula. But because u is not just x, I can't go straight to the formula because du is going to be 3 dx. My problem doesn't have a 3. I need to insert it. So to fully do this problem, I want to rewrite this to get it to look exactly like my formula shows. So I want to have my fraction. All right, a is the square root of 2. Great. So this is a squared. U is 3x. Great. This is u squared. I don't know why I'm switching from dark blue to light blue. But the top is dx. But it's not what I need. I really need a du here. So I need a 3 in my problem and a 1/3 to counterbalance it. And now 3 dx is the same as du. And now my problem looks exactly like the formula. I'm going to do another one of these, and I'll finish this, obviously. But these are tricky, and they're not fun. Well, everything in this class is fun, but you know. I need to notice that this looks a lot like arctan. I need to figure out what a is and figure out what u is. And then also figure out what du is, because du might have a constant that needs fixing or whatever. So in this case, I didn't have any number with dx. I needed to put the 3 in and therefore also divide by 3. Now, this is exactly like the formula shows me. So this is going to equal 1/3 times 1 over a times the arctan of u over a plus c. And now I'm going to go put in a and I'm going to go put in u. So this is going to become 1 over 3 root 2 arctan 3x over root 2 plus c. Duh. Just kidding. So if you were to go back and check this, you should be able to take the derivative of this and it will get you back to that. So let's just do that. I won't do it every time because it's really annoying, but let's just do it. Just to show ourselves, because we didn't go through the proof of this or anything, but just to show ourselves that it works, that the derivative of this gets you back to this. So let's see. The derivative would be, I'd have 1 over 3 root 2 times the arctan of this. So an arctan problem is going to be 1 over 1 plus this squared. So 3x over root 2 squared times the derivative of this, 3 over root 2. Okay, that somehow equals that. Let me see. So I'm going to reduce this. This 3 and this 3 will cancel. This root 2 and this root 2 will become 1/2. Now we've got this fraction. This will become 1 plus 9x squared over 2. Okay, what do we do with this? Gosh, I don't know what to tell you because it's not really fun. Oh no, you know what we'll do? Let's just distribute. Let's just multiply these two fractions. So 1 over 1 is 1. 2 times this stuff, 2 times 1 is 2, plus 2 times this, the 2's cancel, and I have 9x squared. Whoa, check it. Same, Z's. So it all works out. All of this 1 over a, u over a business all works out. Goes a little bit beyond, ours is not the reason why, simply flip and multiply, right? Ours is not the reason why, just realize it's inverse trig, set u's, make du's, put it all in, make it work. There we go. I think that's a good rhyme. All right, for fun, let's try one more. Let's try one with the inverse sine. Oh no, let's try 2 more. Hee hee. Okay, this problem, not obviously, but I could try substitution. I could let u equal 4 minus 4x squared, but du is going to be negative 8x dx. I can put in a negative 8, I can't put in an x, so that doesn't work. So I need something else. There's nothing else really for me to use here except realize, oh wait, this is inverse sine. So let me write the formula up just so I have it. The formula for arc sine is du over the square root of a squared minus u squared. And that's going to equal arc sine of u over a. So let's identify a and u. So a is going to be this number squared, so this squared, so a is 2. U is going to be, and also PS, see how the formula is minus? If this were plus, it doesn't work. That's why they invented things like slope fields and stuff. Don't worry, we're getting to that. But did you know you can only integrate 10% of all functions? So there's so many you actually cannot find the integral of, and you would have to use a Riemann sum, or your calculator would use a Riemann sum with basically an infinite number of rectangles in that space. But there's so few problems we can actually integrate. It doesn't seem like that to you, I'm sure. It seems like we can integrate like all kinds of stuff because there's so many problems for you to do, but we really can't integrate all that much. So again, one little difference, like this is a plus sign, then all of a sudden we can't do it. It doesn't fit any of our models. So maybe that's your task. Come up with some way to integrate it if it's a plus. And I don't know, maybe there is some way, I don't know, but nothing that I know of. Okay, so u, this has to be u squared, so u is going to be 2x. I wish you were in front of me so I could say, everyone understand where I got 2 and 2x? It's because this has to look like something squared, and this has to look like a quantity squared. So this has to become